Hi, Rajaram.
Hi, Arun. We seem to be meeting more often than in the pre-COVID era. I think you've got your internet issues straightened out now, no? Or...
Yeah, this time it is okay.
Yeah, you can never predict actually.
Well, if the power goes off, then there is a problem.
Good morning. Now we are live on YouTube, and also we have a number of colleagues who have joined us on Zoom. Thank you all for joining in. As you are aware, the program is to honor the memory and achievements of Professor Govind Swarup. So here is a picture of Govind at his 90th birthday celebrations, which was held last year at NCRA in Pune.
Little louder, Jasjeet.
So this program today has been organized jointly by ISER Mohali, by the National Academy of Sciences, India, Allahabad, and by the Society for Promotion of Science and Technology in India, SPSTI. So I'll begin with a brief introduction to these three organizing institutes before we launch into the program. IISER Mohali is one of 7 institutes of its kind, which were set up starting in 2006 in different parts of the country to promote education in basic sciences in India. As we will learn during the program, it was one of many of Govind's brainchilds. And of course, it had support and incorporation of ideas from many people. ISER Mohali is now 13 years old. We will be celebrating our foundation day next Sunday. You are all welcome to join us on that day as well. We have at present a faculty of about 100 and about 1,600 students, of which about 1,000 are undergraduate and master's students, and the remaining 600 are PhD students spread across different departments. So I'll stop the introduction of ISER Mohali over here. Society for Promotion of Science and Technology in India was founded many years ago, and I will request Professor K.R. Dharamveer to talk more about it. I'll just mention that their flagship program has been a summer program which they conduct in different parts of Haryana, and recently they have made inroads into Punjab and Himachal as well. So these summer programs for school students are held over about a month-long period. And if I'm not wrong, in the last iteration, they reached close to 2,000 students. So I'll request KRG to say more about the society.
Thank you, Jasjeet Bagla, for giving me the opportunity to talk about SPSTI. Welcome all the speakers. Here's a note on SPSTI which we have prepared. India is a vast country with ancient cultural roots. Its system of imparting knowledge also evolved through the ages.
Your voice is not coming through. Can you please check?
I'm hearing her, Jasjeet.
Is it clear now?
Yes.
Coming.
So here's a note on SPSTI, the Society for Promotion of Science and Technology in India. India is a vast country with ancient cultural roots. Its system of imparting knowledge also evolved through the ages. The modern schooling system, with its mass base, inherited some vestiges from the past.
Dharamveer, we cannot hear you.
Jasjeet, we can hear her.
We can hear. I think you should check something at your end.
Yeah, I can also.
Can you please check your audio once?
Jasjeet, it is okay with us. I think there is some problem at the ISER Mohali end.
Yeah, but he can't hear us either then.
Correct, yeah. So,
can you hear us, Jasjeet?
Professor Arun Grover, who will give us an introduction to about the National Academy of Sciences, India, Allahabad, and we'll come back to KRG after that.
Baglaji, can you hear me now? Dr. Jasjeet?
Well, I can hear very well.
Okay, it appears that others can hear you, and
Yes.
yeah,
I can hear her too.
I have a problem in listening to you. Please go ahead.
Proceed, Kia.
Okay. So we inherited the memory-based learning system. This has stood many of our scholars in good stead, but modern science also requires experimental-based education as one of the major pathways to knowledge. It is generally agreed that our school education is lacking in this aspect. The Indian public is a gullible mass of people, and as a society, we lack informed public debate on issues of importance. Instead, we tend to take the activistic path, be it on the issue of setting up of a nuclear plant, or building of a dam, or introducing genetically modified seeds. The Society for Promotion of Science and Technology in India, or SPSTI, took roots 11 years ago when 37 like-minded people, scientists, administrators, academicians, managers, came together to form this society with the purpose to promote, popularize, and demystify science and technology amongst the masses and to generate interest in these fields, particularly among the new generation. We have launched a number of programs aimed at reaching out to all sections of society. Our regular programs are the Mobile Science Laboratory, which we call the Circus of Science. It is in Hindi, it is called Vigyan Ka Jantar Mantar. This van is visiting government schools of Haryana. You can see a picture of it here, right on top. This is visiting government schools of Haryana in each district by turn. And for past 3 years, it is supported by ST, Government of India, under the NCSTC scheme. We also hold summer schools in science and mathematics for school students, classes 9 to 12, mainly in rural Haryana and also in a few places in Punjab and Himachal. This program is unique in that it utilizes the summer vacation of school students to build their conceptual framework in science. And it utilizes the vocation of many bright students of reputed institutes such as IITs, ICERTs, central universities, etc., by giving them the opportunity to teach in these schools. In the summer of 2019, 14 such schools, 2 to 4 weeks duration, were held. We also have a monthly lecture series by eminent speakers, most of them local or by visiting scientists on a scientific topic of the day. We have lectures on Nobel Prizes. Every year in the month of October, the Nobel Prizes are announced. And soon after, we approach specialists in the respective fields to prepare layman level lectures describing the importance, approach, excitement, and future forecast of the prize of that year. These lectures are delivered at schools and colleges of Chandigarh and are supported by DST Chandigarh administration. We also organize frequently seminars, panel discussions, and workshops on topics of public interest and importance. One such recent event was NEP 2020, the National Education Policy, held on a web platform in association with Nasi Chandigarh chapter. Also on the web platform, we have held poster and essay competitions on COVID, in which thousands of children from many states of India participated. We also held such competitions for IYPT, the International Year of Periodic Table, which was held in collaboration with the Humboldt Foundation. We hold career guidance by highlighting opportunities in the country in various fields of science and technology. We hold lectures by renowned scientists and their discussion sessions with college and university students. These are held at the best known cultural hotspot in town, the Tagore Theatre. We have had professors J.V. Narlikar, T. Padmanabhan, Dinesh Singh, D. Balasubramaniam, Mrigank Sood, N. Satyamurthy, Arun Grover, Ashok Sen, R. Natarajan, and quite a few more. We hold workshops on experimental-based science teaching and also science stage shows. We celebrate important days such as Earth Day, Biodiversity Day, National Science Day, Maths Day, etc., by holding poster competitions, debates, exhibitions, etc., for school children mainly. We participate in exhibitions organized by schools, colleges, and national bodies. To summarize, we are steadily progressing towards our continued goal of taking concepts related to science and technology to the general public through various means, as well as to facilitate and encourage school children to learn through experimentation and exploration from the peer group at top universities and experts in the fields. I conclude by quoting Einstein: contact between the intellectual and the masses must not be lost. It is necessary for the elevation of society and no less so for renewing the strength of the intellectual worker. For the flower of science does not grow in the desert. Thank you, and over to Jasjeet.
Jasjeet, can you hear us?
बागला जी बोलिए.
Yeah, thank you, Professor Kayaji. I now request Professor Arun Grover to introduce talk a little bit about National Academy of Sciences India, and as well as talk about the background to Professor Govind Swarup's coming up from Allahabad University.
Thank you, Jasjeet. I consider it a privilege to have been entrusted the responsibility of addressing all of you at the start of the memorial meeting in honor of Professor Govind Swarup on behalf of National Academy of Sciences of India. Today's meeting, as you have just been told, is being jointly hosted on behalf of NASI Chandigarh chapter and SPSTI. NASI, as is well known, was founded by the invincible Dr. Meghnad Saha during his stay at University of Allahabad from 1923 to 1938. It is a serendipity that Dr. Saha had put forth the proposal of a science academy for the United Provinces of Agra and Audh in 1929, the year of birth of Govind Swarup, in a small town in the district of Moradabad in the present-day Uttar Pradesh. One of the chief objectives of today's meeting is to disseminate information amongst the school and college students and their teachers is that how a motivated student can be enabled to reach global heights by right combination of encouragement and facilitation of opportunities for him or her by the senior scientists. Professor Meghnad Saha elucidated this time and again at University of Allahabad and nurtured a string of good students who went on to become national, and international icons. This process was continued by Professor K.S. Krishnan and Professor Kedareshwar Banerjee, who succeeded him one after the other as the heads of the Department of Physics at Allahabad University. Meghnad Saha, Krishnan, and K. Banerjee, all three had Calcutta past. The latter two had closely done their research work with Professor C.V. Raman. All three were inspired by the great contributions of Jagdish Chandra Bose, Praful Chandra Ray, Ashutosh Mukherjee, and Raman in grooming good students at Calcutta. The mathematician and the High Court judge, Sir Ashutosh Mukherjee, as the Vice Chancellor of Calcutta University, had conceived an algorithm for creating university departments in different subjects on behalf of the university. Substantial contributions from rich lawyers of Calcutta to create chaired professorships and teaching cum research associateships, which could be exclusively given to eminent scholars and promising young postgraduates of Indian origin. Ashutosh Mukherjee invited eminent professors for building schools around them by additionally offering teaching positions to carefully selected university toppers and concurrently encouraging them to enroll for research either on their own or under the chaired professors. We all know that a civil servant C.V. Raman was enticed to accept Palit Professorship of Physics at Indian Association of Cultivation of Science by Ashutosh Mukherjee. Meghnad Saha, Satyan Bose, S.K. Mitra, S.K. Banerjee et al. Were inducted to start teaching an elite batch of MSc Physics students in the newly established College of Science from 1917 onwards. Rest, they say, is history, and it is well documented at numerous places. Nearly a centenary ago, while conferring the DSc Honoris Causa degree to C.V. Raman, Ashutosh Mukherjee had stated, and I quote, "What is still more worthy of congratulations is that a vigorous school of physics has sprung up for the first time in the history of Calcutta University, for that matter for all universities of India, and students from all parts of India have flocked to the laboratories of C.V. Raman." End of the quote. So Professor Meghnad Saha very effectively emulated C.V. Raman at Allahabad. I now enumerate a string of good students nurtured by Saha and his successors at Allahabad in two projections. Mr. Govind Swarup was indeed a part of that string. The notable students of Saha at Allahabad were P.K. Kichlu, D.S. Kothari, G.R. Toshniwal, R.C. Majumdar, and B.D. Nakshalkar. Most of you are aware of the contributions made by all five of them. Kichlu started the honor school at Punjab University, Lahore. After partition, came to Delhi and went on to be a director of NPL, succeeding none other than K.S. Krishnan. Kothari was sent by Meghnad Saha to work with Lord Rutherford in England. He came back and started the physics department at Delhi University, later went on to be the chairman of UGC. Toshniwal, after his doctorate, founded the Toshniwal Industries and he went on to become the president of Institution of Electronics and Telecommunication Engineers. R.C. Majumdar wrote a paper with Meghnad Saha, went to England, then came back and joined D.S. Kothari to build the School of Physics at Delhi University. B.D. Nakshaudhary returned to Calcutta along with Meghnad Saha, but was unable to go and work with Nobel laureate Ernest Lawrence at University of Berkeley. He came back and became a colleague of Saha to set up the cyclotron and eventually succeeded him as the director of Saha Institute of Nuclear Physics. The students inspired by K.S. Krishnan at Allahabad included the famous mathematician Harish Chandra, who was sent by Krishnan to work with Bhabha, the famous theoretical physicist Kundan Singh Singhvi, who first joined Delhi University but went to England and returned to Bombay as a colleague of Bhabha and was the head of the reactor theory group as well as the theoretical physics group at TIFR. He returned at some stage to Allahabad University as a professor ahead to succeed K. Banerjee, but moved away to US. Ajit Ram Verma again was inducted as a lecturer in Delhi University, went to UK, came back to Delhi University, and eventually succeeded uh, Kichlu as the longest serving director of National Physical Laboratory. Govind Swarup is a part of that string. Krishnan invited him to join NPL and then went to CSIR and Australia. And at some stage, we learned today, Bhabha invited him to start the radio astronomy at Tata Institute of Fundamental Research. A contemporary of Govind Swarup, KP Sinha, theoretical physicist KP Sinha, went to do PhD at NCL and worked for his PhD with the then director of NCL, J.C. Flinch. He became a faculty at IISc and he is currently an emeritus professor at IISc. Professor S.K. Joshi did MSc in 1957 when Dr. K. Banerjee was the head. He enrolled for PhD under him, did his PhD with him, and went to US as a visiting lecturer, met K.S. Singhvi at Northwestern, returned to India, and at Roorkee built up the School of Physics at Roorkee and became a director of NPL and as well as the director of CSIR. Professor Joshi, unfortunately, also passed away this year on May 15, 2020. We had held a memorial meeting in honor of Professor Joshi as well a few months ago. So today's meeting is just a continuation of that exercise. So I have also projecting few photographs at Allahabad. This is Meghnad Saha had invited Summerfield at Allahabad. Meghnad Saha had invited Addington at Allahabad. The Indian scientists led by Meghnad Saha and Bhatnagar went to meet Millikan at Caltech just before India became independent. And Meghnad Saha, as you all know, was a part of the first education commission, which was headed by Dr. S. Radhakrishnan. So physicists have played a very important role in evolving the education agenda of India, and we are today celebrating one such contribution of one such physicist. Thank you very much.
Thank you, Professor Grover. It is indeed useful to
I have
know the
concluded,
history.
Jasjit.
And yeah, thank you, Professor Grover. Yeah, so it is very, very useful to know the history and how even in times when there was very little funding available, the heights of excellence in sciences were achieved by a few dedicated people, because now we can definitely do better, and it is important to learn from the past. Now I'm going to request Professor Kulinda Pal Singh. He started his education in Patiala, and then he went to Tata Institute of Fundamental Research for his PhD, where he became a faculty member, and he continued working there. He has contributed to astronomy research in a very wide variety of fields. He was associated with the group which along with Professor Ajit Kembhavi, which started looking at the use of charge coupled detectors in optical astronomy. He also tried his hands at radio astronomy in Ooty, and he was very deeply involved in the AstroSat mission, where he built the soft X-ray telescope for the AstroSat, which has been functioning very well. After retiring from Tata Institute of Fundamental Research, he joined us at IISer Mohali about 3 years ago, and it has been great having him here. I request him to give a biographical introduction to Professor Govind Swarup.
Thank you, Jasjit. It's indeed an honor to give this talk today, although I didn't have much personal knowledge of Govind Swarup, but I learned a lot while preparing this, and I have drawn heavily from an article in the Journal of History and Heritage. Two gentlemen, I'll refer to that later. So, good morning, everyone, and I'll begin my talk of a little small bio sketch of Govind Swarup that I have put together from the information available in the archives. So here is the picture from, I think, last year or very recent picture. And so Govind Swarup was born in Thakurdwara, which is a small place near Moradabad, 23rd March 1929. And his grandfather was a very big landlord. His name was Brijpal Saran, and he owned a textile mill and lived in a mansion. In 1895, he had graduated in philosophy from Allahabad University and was fluent in Persian and English. Govind's father was Ram Raghuveer Saran, established the first theatre in Delhi and started a motor car garage and purchased land for farming. So he came from a pretty rich family also. His mother was Gunbhavati Devi, a housewife. She subscribed to an Indian magazine, and she was the one who encouraged Govind to read. So this map on the right displays the various places that he was, Govind Swarup was associated with throughout his life and so on. And we'll see this sketch as we go on. Now, it's very interesting. I came across this thing that he actually occasionally rode an elephant to school. I don't know if you can see the picture of the elephant on the right in the screen. And which was bought by his father to go to the farm during the wet season. But whenever there was no work for the elephant, it was available for Govind to go to school. It just reminds me, some people are born with a silver spoon and some people are probably born with the elephant in the attic. And this was in Moradabad, where the family had moved when he was 12 years old. Govind's personality began to develop while he was at a Coronation Hindu high school in Moradabad, and this is where he learnt English. So he matriculated in 1944 with distinction, and then went to Ewing Christian College so he was around 15 years old. This is the Ewing Christian College in Allahabad, where he went, and apparently he mentioned that he learned to swim in the Sangam in Allahabad, and which came quite handy when he went to Australia, apparently working on the Potts water reservoir, Pottsfield reservoir. So he became a secretary of the college physics club and was the one who invited Professor K.S. Krishnan to deliver a lecture at the college. And this was one of his kind of turning points later on in his life. And he moved to Allahabad University after doing his 2 years college, or the college thing those days. And his teacher was, of course, Karyamanikam Srinivasan Krishnan, popularly known as K.S. Krishnan, who had been knighted in 1946, same year, and who in 1947, in Independence, accepted inaugural directorship of the Physical Research Laboratory in Delhi. So Govind Swarup did his BSc here in 1948, and he finished his MSc in 1950 here. In 1949, 36th Indian Science Congress was held in Allahabad. So at the time, C.V. Raman was attending this Congress, and so he invited C.V. Raman to come to the hostel to give an evening lecture, and C.V. Raman agreed, provided he says a condition that all students must come and attend his lecture first, and so on. Which of course was followed by a small dinner in the hostel with him. He also took, during this Congress, a British mathematician and geophysicist, Professor Sidney Chapman, showing him the Allahabad city around and so on, and he wanted to see that place. And after finishing his MSc in 1950, he went went and joined K.S. Krishnan at NPL, who asked him to develop an equipment to investigate paramagnetic resonance with condensed matter at a wavelength of 3 centimeter by saying, you cannibalize these surplus radar sets which have, become quite available. Apparently, these radar sets played a big role everywhere for radio astronomy. And these were procured by the NPL, and he then went about looking at them, and also said that he found a remarkable set of 28 volumes of the Radiation Laboratory series, and he studied parts of them. And these describe almost all the radar techniques that were developed during World War II. In August 1952, when he was still at NPL, a 10th General Assembly of the International Radio Scientific Union, URSI, was held in Sydney, Australia, and K.S. Krishnan attended almost, most of the radio astronomy sessions in that union, that meeting. And he was impressed by what is going on, and he wanted to launch radio astronomy program at NPL. He came back and he told Govind that I want you to go and learn from Australia. There's a very good group. So he sent him as an apprentice at the Division of Radio Physics in Sydney through a Colombo plan. That's a very interesting thing you can look up in the Wikipedia. This was actually a brainchild of India's first ambassador to China, Mr. Panikkar. And he was very successful in getting all the Commonwealth countries, including US, to fund this heavily, under which dams, bridges, roads, lots of things were built in these emerging, developing economies from Lanka, and, India, and so on, and other Commonwealth countries that got free. And the other person who joined him to this as an apprentice was Mr. R. Parthasarathi from Kodaikanal Observatory. Now, at that time, the leader of radio astronomy group within the CSIRO division was Mr. Pausi, Dr. J.L. Pausi, who played a very leading role in, his development later on, and guiding him on where to go, what to do, and so on. And he was very impressed by Govind Swarup's, young Govind Swarup's, work in Australia. So, of course, the rest is history. Wait, and a few more slides to go. And so here is the Potts Hill field station around these water reservoirs. And you see on the arrays, which are at that time known as grating arrays for studying the sun. And these are some of the places, as you see here in the previous map, around Sydney and so on. There are a lot of facilities were built during that time. So this was one of the facilities. There were actually 7 or 8 field stations around this place, and Govind went to work there along with Parthasarathi. And it was all based on the solar field that you will hear from Divya O'Brien. Okay. This is one of those grating these dishes here. And here is a picture of Govind and Parthasarathi. Apparently, this picture has come from Illustrated Weekly Times of India, 1954, and not from any archives in Australia or India. So it's quite a rare picture. The two of them actually working on one different instrument, which is for which they developed a 45 megahertz receiver, and they were already starting to look at scintillation experiments, because one of these big guys in Australia had found that the Cygnus A is scintillating, and that is 1952. And so this was a kind of beginning of interferometers. It also asked to make a phase shifter between the grating arrays and so on, so that the temperature effects could be taken care of. So this was apparently this 45 megahertz receiver was a big thing, which was later used by various people in Australia. Of course, Govind has left them. And so on. So he returned in early 1955, and that was the beginning of a radio astronomy group at NPL, and a lot of people joined. T. Krishnan, not a relative of K.S. Krishnan, who was working on the Martin Dial PhD and came from Cambridge University. Parthasarathy left Kodaikanal Observatory, joined NPL, and M.N. Joshi, MBG Sarma finished their PhDs, MSc degrees in India, and Mukul Kundu. These are all basically MSc people at this stage. They have not gone their PhD yet. And they began this radio astronomy group at NPL in 1955. But this did not last long because before coming back to India, Govind Swarup suggested to Pausi that how about sending this one of these arm of that array on that reservoir with some 32 dishes to be gifted to India, and Pausi had agreed. But when he came back and he wrote to Krishnan saying that this is the gift and why don't you arrange to get it transported back to India. But the government of India refused to pay for the transportation of the dishes, and everybody left. Within the next 2 years, everybody left. Although it turns out that 2 years later, the Australians agreed to pay for the transportation, but that was too late. Govind left for US in December 56, just soon after getting married, and he went and joined this observatory, the antennas in Fort Davis in Texas, which were run by Harvard College Observatory. And here, then he discovered a rare U-type burst from the sun in 1956, which was eventually published in 1958 in Nature, and one of I think Divya will tell you more about these things. Here it is, they call U because it's the frequency on the y-axis and the time on the right axis. So the 8-second burst in the sun, and it follows this U shape in the frequency, and so on. Here's a picture of Maxwell, who was a co-discoverer of this thing, Swarup and Goldstein, and this is the 28-feet dish at Fort Davis. So, now, he wanted to do PhD at this stage. He decided that enough for his career, it's important that he get a PhD degree, and he wrote to Pausi, and Pausi wrote back. He says, which place should I join? And this is what Pausi told him, that Stanford is famous for radio engineering, Caltech for physics, and of course, it's astronomy research, and Harvard for training in astronomy. If you are planning to return to India, I should recommend you to a place with great emphasis in electronics. It is a key to open many doors. Now, he had actually got a lot of experience in making receivers and so on at that stage. So he went and joined Stanford in 1957 for his PhD based on this advice, and he worked on this array, the cross grid array in Stanford, which had just been started, and so on. So he was, instrumental in getting this up and running, and he made a breakthrough in how to do phase compensation scheme to compensate for the temperature effect during the day, because this place, in near Silicon gets very, very hot in daytime. So, as soon as he got his PhD, he was offered assistant professorship in electrical engineering at Stanford on 1 Jan 1961. I think he got his PhD in 1960, late 1960, and he continued. But he was keen to come back to India. So on 23rd September 61, 4 people got together who were at some stage together, this is T. Krishnan, and in NPL, a few years before, they wrote a 3.5-page proposal titled "A Proposal for the Formation of Radio Astronomy Group in India," and they sent to 5 government organizations in India: Atomic Energy Commission, Baba was chairman of both director of TIAFA and chairman, UGC, NPL, CSIR, and the Ministry of Natural Resources and Scientific Research. Now, this bureaucracy in the government thing, they sat on it, but Homi Bhabha was very quick. Within few months, on 20th January 62, he sent a cable, telegram, and he asked Govind to join TIAFA, who came in March 63 and joined TFR. Immediately, there were 4 young people who had just joined TFR under various graduate school program. At that time, I think BRC school program, and JD Islu, Kapahi. He joined first, then Kapahi, then Bagri, and then RP Singh. And they then went on to install 24 1.8 meter diameter dishes. They built them and installed them at Kalyan. And this is from the archives in TFR archives. This picture, old picture, somehow this, both the land and what happened to this has all, has no history left. It kind of disappeared, unfortunately. And then on to Uti, you will hear about these things. This is where I met him in 70s, mid-70s, when there was a Astronomical Society of India meeting, and he had put in this, apart from this long dish, which was actually, completed in 69, to carry out lunar occultation and also to study the sun. So lunar occultation of, point sources, quasars types, and so on. In 76, he had put small 4 mini cylinders. This is a half a kilometer long on a slope hill that matches the latitude of Uti, and thus for easy for tracking and studying all these things. And there was the inauguration of what we call the synthesis telescope, and that's where I got into a little bit of radio astronomy later on, 10 years later, and started probably one of the first observations of clusters of galaxies in 86, 87, using this 4 cylinders and the forerunner to Jmrt, basically synthesis telescope with interferometer and so on. And this is the Jmrt that you'll hear again a lot, and which was completed in 99 and became, now it's been upgraded. You'll hear from Yeshwanth a lot of things about this. And I think that's where I'll stop. And I really want to acknowledge this article, which is a wonderful article, a detailed 40, 50 page article about Swarup, which was actually on his 90th birthday. And have liberally taken this material from there. And so I think people can read much more detailed about what was going on in Australia, with the leaders of radio astronomy at that time. So thank you, everybody. And I will stop here.
Yeah. Thank you, KP, for this nice overview. We now move to the next speaker, Professor Rajaram Nithyananda. Rajaram studied in Madras, now Chennai, and then moved to Bangalore for his PhD in the National Aeronautical Laboratory. Now it is called the National Aerospace Laboratory. After that, he joined the Raman Research Institute as a faculty member, where he remained for almost quarter of a century, and then he moved to National Center for Radio Astrophysics, NCRA, in Pune, which manages GMRT as the director of the National Center for Radio Astrophysics. At present, he is at Aziz Premji and continues his interest in science education, astronomy education, and a number of things. So, Rajaram, over to you.
He has to unmute.
Rajaram, you're muted.
Has to unmute. It got muted again. Yeah. You naturally think of the Uti Radio Telescope, GMRT, and Govind's stay in Mumbai and in Pune, and of course in Uti. But there is a very interesting phase of his stay in Bangalore, but even remote influence on science and astronomy in Bangalore. And I'll try and bring that out. And this is something which I personally witnessed at first hand. Of course, we are talking of a many-sided personality like Govind. So clearly there's a lot more to him than what I will be telling you. But this is a different side, going beyond his own institution and creating, I would not even say institutions, but programs in which many people participated and which had a big impact on astronomy in the country. Now, I'll start at 1972, which is just a few years after the Uti Radio Telescope was completed. Govind was able to hold a summer school, a very advanced summer school in radio astronomy at the Indian Institute of Science. Of course, his group of young people, you already heard of Vijay Kapahi and many others, Pramesh Rao and so on, were all there. I was a research student doing optics and crystallography in the material science division. But in those days, Bangalore was a small city. If there were some very nice lectures in the Indian Institute of Science and you had a very liberal thesis supervisor, he'd say, go and sit there. So I sat in the back row and listened to these outstanding astronomers, two from the US, one from UK. And I think I followed what they were saying, but my main interests were a little different. Okay. However, when I moved to the Raman Research Institute, I was again getting involved in astronomy, and then I appreciated the caliber of this summer school. It was absolutely by the best experts on very contemporary topics. This is just an early example of the academic side of Govind, of getting people together and absolutely at the cutting edge of the subject. Now, there is another side, which is encouraging young people to enter astronomy. And he was very quick in taking initiatives in that. So just a few years later, 1976, he took the initiative, realized that a lot of people are not coming into astronomy for lack of exposure, since astronomy is not taught in the master's level or bachelor's level. So he said, let's have an intensive summer school. Let's expose them to all aspects of astronomy. So there's nothing narrow about Govind, that he only was interested in radio astronomy. So this was hosted at the Raman Research Institute. And this was in 1976. And that summer school was a pretty amazing venture because literally, it had about 20 students, but almost half of them went on to careers in astronomy and did very well. And what is even more interesting is the faculty of the summer school included people like me who didn't know much astronomy. So Govind would say, okay, you're lecturing on such and such a topic in this summer school, so go and read it and understand. And this is his infectious enthusiasm. It's impossible to say no to Govind. His persistence and his persuasive powers. So not only did he promote astronomy amongst the students very successfully, of course, it was a one-off effort, right? That particular batch of students benefited. A few more summer schools were held. And then he conceived of something which was even broader, saying that, okay, let us say we have attracted students to do a PhD in astronomy. Because, again, these students come from physics and engineering, and they need to bring this all together to make an impact in astronomy. And they also need, he was much ahead of his time, a multi-wavelength exposure. You don't just join an optical observatory and learn about optical astronomy or radio or anything else. You really want a broad training. And so he conceived of the joint astronomy program. And I'd like to share screen at this point. Okay. Can all of you see the slides?
Yes.
So this is the. So I talked to you about the summer school, which was held at the Raman Research Institute, which is shown here, and the earlier 1972 summer school, which was held in this beautiful building, which used to house the physics department at the Indian Institute of Science. Okay. But now I would like to tell you about the Joint Astronomy Program, which has been a very successful venture in attracting bright students to astronomy, in giving them the right training, and then giving them opportunities to work in the best institutions in India. And this was, of course, a joint effort, but Govind had a very major role to play in it. Even though he was at this time also having his hands full in developing the UT radio telescope, developing that group. We are talking of around 1980. But you can see his broader vision here. And of course, there were people of a very high caliber who recognized that this was a great idea. Yes, Professor Dhawan, who was the director of the Indian Institute of Science, and of course also the father of the Indian space program, Govind himself. V. Radhakrishnan is a radio astronomer who came to India in 1972, so almost 10 years after Govind, right, to head the Raman Research Institute and started a group there. And I will later on be telling you much more about the interaction between these two groups. But specifically in the Joint Astronomy Program, the small group at the Raman Research Institute took an active part, as did the group at the Indian Institute of Astrophysics, again led by a very distinguished astronomer who unfortunately died very young, Professor M.K. Vainababu. And again, look at the vision that realizing that space was going to be important to astronomy, Govind was able to persuade Professor U.R. Rao, who headed the Space Research Organization in Bangalore. And therefore, the first students who joined this program actually had a unique opportunity of exposure to every branch of astronomy. And if there were branches of physics which are needed for astronomy, like fluid mechanics or celestial mechanics, some of the best faculty in the Indian Institute of Science were exposed to it. So I personally think that the students in this program got as good an exposure and training as they could have got anywhere in the world, perhaps even better because of the diversity. And the amazing thing is that all these institutions work together smoothly. And the Indian Institute of Science, I do want to single out the fact that at that time, the physics department did not have even a single astronomer there. But the physicists in that department, encouraged by Professor Dhawan, gave their full cooperation. And of course, then the department did hire astronomers. Now they have quite an active group of half a dozen people, and they take their own research students. But in these early days, these research students, after 1 year, would go around, and some of them would join UT, some of them would join RRI, some of them would go to space, some of them would go to IA, some of them would even go to PRL. So this was a pretty amazing collaborative program. And while many people deserve the credit for it, I think Govind's unique personality acted as a kind of catalyst. Okay, a catalyst is something which makes a reaction go faster. And those of you who have known Govind know that he would not let grass grow under his feet. He wanted things to happen immediately, but he was able to persuade this galaxy of people that this was worthwhile, and his vision is fully justified. I think this program has been extremely successful. In fact, the first batch of that program are now retiring from their own careers in places like Ayuka, TIFR, and so on. And they in turn had their own students. And this model of very wide training in astronomy was also adopted later in Pune. So I would say that this is a fantastic contribution by Govind, which was based in Bangalore. And it just shows a broad academic vision, while at the same time, he was not just doing this. You will hear about the UT radio telescope and the Jmrt and so on. So now I would like to turn to the other major events which occurred in Bangalore. And this was the collaboration with the Raman Research Institute. Now, I mentioned to you that Radhakrishnan came after the demise of C.V. Raman to head the institute. And being a radio astronomer, he naturally wanted to set up a group. But he visited UT, and I've heard from Govind and also from RAD, RAD being the abbreviation for Radhakrishnan, that Govind very generously said, look, you can come and, till you get all your own telescopes up, you're welcome to start some program at the Ooty Radio Telescope. Okay. And of course, Radhakrishnan, like Govind, appreciated the importance of electronics. So this was not just going to be to come and use the telescope. It was going to be to set up a state-of-the-art electronics lab and build receivers for the specialized application which they had agreed would be pursued at the Raman Research Institute. So first, who came to head the electronics lab at the Raman Research Institute? None other than one of Govind's senior trusted colleagues, NVG Sharma. Okay, so Sharma, you have already heard earlier, was in NPL. Then that group disappeared, disintegrated, rejoined when Govind started at TIFR, contributed to the building of the Ooty Radio Telescope, which you will, I hope, again hear about. And then, after 10 years, they moved to the Raman Research Institute to set up this lab. Okay, and of course, that lab also started working on other radio telescopes, which the Raman Institute was interested in, but also built this line receiver. A little bit of science background here. The Ooty frequency of 327 megahertz or wavelength of 92 centimeters is a protected frequency for radio astronomy. And one of the reasons is that a neutral atom of deuterium would emit. Because deuterium is a very rare species compared to hydrogen, but there's a lot of interest in knowing how much deuterium is floating out there in our galaxy. So that is the reason why this frequency is protected. Even today, there is just, Rajaram can say more, but I would say there's a marginal detection of deuterium in interstellar space. So in that sense, looking for this line has only put upper limits. The first effort was by Sharma and Mohanty at Ooty, and the next effort was by Anantaramaya, or to giving his full name, Kuduvalli Ramaswamaya Anantaramaya, who was Rad's student, perhaps his favorite student, who took up the study of first deuterium, which became an upper limit, and then the study of what are called recombination lines. So recombination really means electrons which are initially free, getting bound to a hydrogen atom and gradually coming down the ladder. So if they jump from n equal to 273 to 272, they emit at the frequencies which the Ooty Radio Telescope. And here they were able to do some very pioneering work. And interestingly, just to give you a feel for the back and forth between these two groups, Ananta did his PhD there. And of course, he was hugely influenced by Govind and by the atmosphere of that group. I think he was practically recognized, welcomed as a member there. And because of him, many of us also got drawn in and spent time in that group. And I would like to think that whenever any members of that group were in Bangalore, they walked into the Raman Institute, not as some strange place, but as a place where they felt at home. And this kind of collaboration was really remarkable. So on the same field of recombination lines, while Ananta did a major thesis on it, later on, a young man at Ooty, Anish Roshi, wanted to pursue it further. And then he would frequently come and work with Ananta. So another example of this fruitful scientific exchange I would like to mention is that one of Govind's brilliant students called C.R. Subramania actually came up with a very novel way of processing the data generated by the Ooty Radio Telescope. Now, the word lunar occultation was mentioned, and what that really means, and which is the primary program of the Ooty Radio Telescope, is that the moon covers up a radio source. You don't just see a simple step. You see a complicated pattern because of the wave nature of radio waves. And you have to infer the nature of the source from this pattern. And this is a very interesting mathematical problem to which there was a classical solution, but C.R. Subramania came up with a better solution. And it turned out that while solving this problem, he was again ahead of his time, because only many years later, the rest of the radio astronomy community realized that these general ideas which he introduced would actually have impact on many problems in image processing. Now, C.R. Subramanian actually published his results quite late, 1979, but thanks to this overlap, many years before that, many of us in the Raman Institute learned of his ideas, and some of us were able to take it further. So I'd like to mention Rajan Bhandari, Ramesh Narayan, and me too. And this area is called maximum entropy image reconstruction. And the idea is again to say that how Govind kind of created a fertile atmosphere between these two groups. And a lot of good things came out of that. And a lot of good personal relationships and friendships came out of that as well. But this entered a new phase when many people from Ooty actually moved to Bangalore. So in fact, let me see if I can show you one more picture. Tata Institute of Fundamental Research had a center in Bangalore called the TIFR Center. And yeah. Yeah. So here's that center. And initially it was populated by mathematicians. And then the radio astronomers came in. And by then, Govind had conceived of the Jmrt. And a lot of planning, a lot of discussion took place. And the RRI was just a couple of kilometers away. So one very important development took place at this time. The Jmrt was optimized for a wavelength of around frequency of around 600 megahertz, wavelength of 50 centimeters, right? Because that was the wavelength at which it was believed at that time you might see signals from clouds of hydrogen before they formed galaxies. Now, as it turned out, the cosmology changed while the telescope was being built. But in any case, this was the most sensitive frequency. That, and of course, the Ooty frequency of 300 megahertz. The Jmrt is a remarkable story in itself. All that I will say is that if you want a telescope to work at a shorter wavelength, then it becomes more expensive. The surface has to be more accurate. The machines which move it around in the sky have to have greater accuracy. So all this costs money. And Govind had a limited budget, and he wanted to get the best telescope for his science from that budget. So he was not very interested in shorter wavelengths. And one very interesting shorter wavelength is around 21 centimeters and a little longer, where the more abundant species of hydrogen, I mentioned deuterium earlier, but just normal hydrogen, which is abundant in interstellar space, both emits and absorbs radio waves. So naturally, having got that close, various people said, can this telescope be stretched? And it turned out that Govind's design was so good that this telescope even had significant performance without great loss of performance, some loss, at 21 centimeters. But Govind was very clear. He did not want to be distracted from his main goal, but he was generous enough to say that, look, if people want this, someone has to come forward to build the receivers for that, because we are going to have our hands full in building the telescope and building the receivers for the longer wavelengths where our science lies. Well, that turned out to be very fortunate. And the person who stepped in, the laboratory which stepped in was none other than the laboratory which his old colleague NVG Sharma had set up at the Raman Research Institute. But this was not a case of building one receiver. One had to build more than 30. And they had to, of course, fit in with the whole Jmrt program. So I was a witness, though I was a theoretical person, but RRI encouraged a lot of interaction between theory people and the electronics lab. And I witnessed this major effort going on. It is major for RRI, which is a relatively small institute. I do want to emphasize that the efforts which are going on at Pune, but of course on a much grander scale. And I hope you will hear something about that. Okay. So I think the other name for these receivers at around a wavelength of 20 to 30 centimeters is L-band receivers. And you'll hear about the science of these L-band receivers, I think, from Rajaram. it turned out that this was very natural for RRI to take up, because the study of the 21 centimeter radiation from hydrogen was one of V. Radhakrishnan's major interests when he was in Australia, and he continued it to some extent, though we didn't have a telescope even in the Raman Institute. His other major interest was pulsars. So one first generation piece of equipment for pulsar receivers was built in the Raman Research Institute labs. Of course, a lot of things have happened since then, and you'll hear that from Yeshwanth Gupta, right? So, so this continued, and I should really, Govind moved to Pune naturally as the Jmrt came up. So I just want to conclude by mentioning Govind's, I mentioned his impact on the Joint Astronomy program and on the collaboration with RRI. And I'd like to conclude by mentioning the personal impact on me. So as I told you, I was a theoretical astronomer sitting in Raman Research Institute, but looking over the shoulders of my observational colleagues, talking a lot to members of the UTI group. And I guess I would have continued peacefully like that. But sometime in March 2000, I was asked somewhat mysteriously by Professor Jha, the director of TIFR. I knew him. I had attended his lectures on superconductivity. He was a kind of father figure to theoretical physics. So he said, just come to the TIFR center. So I went to that building whose picture you saw, and he led me into a room. He said, just listen to everyone. You don't have to give a quick answer. And sure enough, Govind was sitting there. And of course, this was the outcome of a tragic event, that Vijay Kapahi passed away due to cancer a few months earlier. And I think Govind was part of this group who were going to look for someone to take up the sort of administrative head, but hopefully a scientist who take that up. And don't ask me why they asked me, but the important point is, why would a person like me move to take up a job for which I really had no experience? And I guess the answer is, again, over the years, when I built up such a respect for Govind, for the achievements of him and his group, and also one didn't feel like a stranger amongst these people. I hope they didn't think that I was a stranger coming from Bangalore. So that began another decade period of my life, which is in Pune. But that's very much the story of the Jmrt, which will be told by the younger people. So here I would just stop by saying that quite apart from these two major telescopes and building up his own group, Govind is in some sense a statesman for astronomy in India, which you can see from this collaboration between two institutes. I forgot to mention that there is not a single piece of paper you can find, no memorandum of understanding. I think when you have real understanding, you don't need a memorandum of understanding. And the Joint Astronomy program. So this is the other side of Govind, which I would like to bring out. And also his personal impact on many of us. Okay. In fact, the back and forth did not end with my moving to NCRA in Pune. When the Raman Institute was looking for its own director in 2004, the choice fell to Ravi Subramanian, who was Govind's student at UTI. Okay. And then I told you Anish Roshi moved to the Raman Institute. So I'm happy to say that NCRA will probably get him back. And C.R. Subramania, who had done so much nice work for 30 years in NCRA, moved to RRI, where he continued to do very innovative things. So I think this is a very unique phenomenon of building a community, a close-knit community. I do hope this community goes forward and achieves great things, perhaps as part of the square kilometer array and so on. And I'd like to stop here.
Thank you, Rajaram, for this very nice overview. I will now request Professor Ashok Singhal to speak about the UTI years and the UTI radio telescope. Professor Ashok Singhal is at PRL post-retirement. He had done his master's from Punjab University, Chandigarh, and then he joined the radio astronomy group in UTI, TIFR and UTI for his PhD. He worked there for his PhD and later on as a faculty member in the group till 1987. And then he moved to the radio astronomy group in Bangalore for a few years, and then on to NCRA before going and spending some time in Bonn, and then in Dwingaloo, and coming back to PRL in 1995, where he retired. Ashok's interests are not limited to radio astronomy or even astronomy. Particularly post-retirement, he has taken keen interest in science education and basics of physics, and he has been writing a number of interesting expository articles on physics education. So over to you, Ashok.
Hello.
Yes, Ashok, we can hear you. You can. Would you like to share your screen?
Yeah. I'll first show a picture of UT telescope, which KP already showed some part. As you can see, UT telescope is made on a hill, which is a slope of 11.5 degree, which is actually latitude of the place. See, if you make a telescope on horizontal on equator, it will be parallel to the axis of Earth. But if you go to the pole, North Pole, let's say, and you make a horizontal telescope, it will be a 90 degree to the axis of Earth. But at the other latitude, if you raise the telescope slope to equal to the latitude of that place, it will become parallel to axis of Earth. So that's what is done, and that was a unique design which Swarup had in mind, and would make the telescope much cheaper, perhaps order of magnitude cheaper than the similar area telescope. And the telescope, of course, started working February 1970. I think 18 February was the first observation. But unfortunately, within a year or so, there was an accident. I don't know, many people may not know about it. It was a stormy night, and somehow the shaft of the telescope, you can see the red shaft, the center, that shaft broke, and perhaps around 1/4 of the telescope rotated, and the other was not rotating. So the whole thing, the front thing, what you see is the receiver system, truss line, that got twisted and broke. Now, any lesser person like me would have given up and maybe gone back to his father's business, but not like person like Govind. He, and of course, all his group. I joined actually later when the telescope was being rebuilt. So they took 3 to 4 years, maybe 5 years to rebuild the whole thing, some mechanical thing, as well as the electronic. And perhaps I can show my arrow if it's visible. This thing is called counterweights, which were earlier not there. And the new design, these were put. And then telescope has been working fine. Now, but Govind was not the person who will sit on his laurels. As soon as telescope ORT is called, UT radio telescope, as soon as ORT was ready, he started thinking of further. He started thinking of something called OSRT, UT synthesis radio telescope. Now, in radio astronomy, if you have many telescopes, you can combine the signal from them, and then you can get resolution, which is the maximum separation between those individual elements. And here, telescope like a big mother, UT telescope like a big mother in the center, and some what we call baby cylinders around it, or even some dishes, parabolic dishes. You could get a reasonable signal, and you could get better resolution and make maps of radio sources in sky. That was the idea. In any case, so this went on for many years. I'll say somehow due to logistics and other problem, the experiment was not that successful, but it added to the experience of the group. And from that, of course, that experience later showed up in Jmrt. And then Swarup started thinking, why not design another telescope, which is of international collaboration, which should be similar to UT telescopes. This is called paraboloid cylinder, a cylindrical parabola, because in north-south axis is like a cylinder, and the east-west is parabolic shape. So he thought of something which can be built on the equator of the Earth, because making similar big telescope on a slope is much more difficult. So he called it GERT, Giant Equatorial Radio Telescope. In the process, he also had a UN-sponsored workshop in Uti, where many people came, including Nobel laureates. And but then there was a lot of politics, international politics comes in. Of course, he had Nigerian people, but Equator was not exactly passing through Nigeria. So then he got Kenya, he also had Brazil in mind, he also had Indonesia, where the equator passes through. And he had a good reception, but still things were not progressing well. And then he was wondering whether we should make similar thing in India itself, forgetting the international collaboration. And then he started thinking what he started calling, that time it was not called Giant Meter Radio Telescope, but later the name was Jmrt, Giant Meter Radio Telescope. And initial thinking was to make cylinders, similar like Uti telescope, but then of course, if you move somewhat northward, like a place later selected Narayan-gaon, but earlier something near Bangalore was also in mind, and also in Indore. Then as you move northward, the finding or making such a telescope parallel to axis of Earth becomes very difficult, almost not practical. So he was wondering what to do, and then some development took place in Uti telescope, actually in OSRT, Uti Synthesis Radio Telescope, which I think changed his mind. The thing was that Uti Synthesis Telescope, we were making some maps. I was not directly involved, I was writing my thesis those days, but still I was around. And then many people like Velusamy, Pramesh Rao, and Sukumar, many others were involved in that. And then they found if there is some phase gradient across the maps of something end-to-end 50 degree or something like that, which they were not able to resolve out, not able to take out. They did so many experiments, so many observations, but they were not able to take it out. So I, in fact, was once in control room, and Velusamy and Parmesh, they were just discussing this. I just happened to listen. So then I asked what happened and all that. They sort of ignored me, but they said, okay, there is some phase gradient like this of around 50 degree. Then I was just thinking of that, and then I somehow thought it may be due to the main Uti radio telescope, which was asymmetrically placed with respect to its rotation axis. This is asymmetric parabola. So this is not, so it's the red axis shaft is not right at the center of the parabola. So somehow I thought that may be causing this. And then I took out the what you call blue maps, not blue charts or something such a word is used. Okay, blueprints of the design of the Uti telescope from the library, and then exactly made some measurements. And as you can see, there's this reflection. You can see this sunlight reflection. There are 1100 stainless steel wires which make the surface of the Uti telescope, and their placement and separation, that was all entered in that. I took all those values and tried to find the sort of center or centroid of the telescope. And then I found it is at least 5 or maybe it is more, 8 centimeters away from the center of the axis of the red shaft, rotation axis. And then I thought that may be the reason that this phase gradient coming. I talked to Swarup and he was interested. Then I worked it out and whole group was called and I showed it on the blackboard and also wrote a internal report. So it turned out that yes, that was the reason. But then that put off Swarup from cylinders. He thought, no, cylinders are no good. Although I was arguing, this is only because this is not a, this is asymmetric parabola. That's why it's problem. But he said, no, we will not use cylinders. And then he thought we should use the paraboloid dishes. And then of course, equator was not a requisite for that. And then he really thought we should make in India only. And then of course, various sites were explored and finally near Pune, Narayan-gaon was the place which was selected. And that's how the Jmrt came up. Of course, I was involved in Jmrt for about 2 years, like in the configuration studies, where to keep the antennas, and Swarup and Anantakrishnan, they'll go around and find, okay, some place is not good because there is some road is nearby. Then we try to understand how much interference can be there. And then there's somewhere वो जैसे कहते हैं हिंदी में नदी नाले पहाड़ काफी चीजें थी. So avoiding all those, they'll tell कि okay, this is roughly the area, and then I try to optimize. So it took me about 2 years. In fact, I had just written my thesis, but I gave it to Swarup, but he was, of course, a tough man, although he was very gentle also. He said, first we must figure out the configuration of Jmrt, then only I'll sign you a thesis. So that's fine. That motivated me to work harder on that. So then we had Jmrt configurations sort of worked out. Of course, I had not been to Jmrt site while the time of building too many times, only twice I had been. That was to fix the north-south line, to locate the pole star. I was familiar with the little bit of sky. So many other people will come with me using theodolites and all that. I'll point out, okay, there's the pole star. And that's will fix the north-south line. And later, of course, I spent a year or so in Pune before moving abroad. So that was the sort of person who will not sit on his laurels, and he will not give up early. So that's all I like to say. Thank you.
Thank you, Ashok. Thank you for your presentation about the UT radio telescope and movement towards the GMRT. Now I will request Professor Ajit Kembhavi to talk about the early years in Pune as the group was transitioning from Bangalore to Pune for the GMRT and coming up of IUCA, as well as the program being run by the Tata Institute of Fundamental Research in collaboration with the University of Pune. Professor Ajit Kembhavi was born in Hubli, Karnataka, and he had his early education there. Went to Mumbai for his bachelor's and master's, and he joined Tata Institute of Fundamental Research, where he worked with Professor Jayant Narlikar for his PhD. After a postdoctoral work at Institute of Astronomy in Cambridge with Professor Martin Rees, he came back to TIFR, where he remained until IUCA was set up, and he moved to IUCA in 1988. He was the director of IUCA between 2009 and 2014, and he continues there as an emeritus professor. Ajit has made very significant contributions to outreach of astronomy to universities and getting universities and colleges involved in astronomy research. One of his one direction in which he has contributed significantly is the development of a virtual observatory where a lot of data, archival data, is made available in a manner where it is easy to use for astronomy research. And another, which is less well known, is how he managed to get journal subscriptions for a lot of universities and colleges working in along with the UGC, so that researchers in colleges and universities had access to a lot of research, the ongoing research at that time. So I request Professor Ajit Kembhavi to take over now.
So good afternoon. Thank you, Jasjit, for introducing me. I can say that I'm honored to be here in this meeting, but speaking at this meeting, but I can't say that I'm happy, because I would rather have Govind amongst us than speak in his memory. Now, people have already talked quite a lot about how Govind was and what he did. So I will keep my account very personal and about some interactions we had right from when I was a student to having to the IUCA NCRA days. The last time I met him was in Yeshwanth's house for a dinner, which was about 6 months, just before COVID, I think. And so, so the first time I met him was sometime in 1972. So it was a very long association of 48 years. Now, when I joined TIFR, then at that time, there was a shortage of students in the institute, and various people used to call students to join them. And Swarup had heard about me and one of my colleagues from Bombay, and then he asked both of us to go to Ooty. But at that time, I said that I was thinking of working with Jay, who was still not in TIFR at that time. He was in Cambridge and had to come and join. That seemed like a very long shot. But anyhow, I stayed in TIFR. Then another occasion when Swarup asked me to go to another city, that was to Bangalore, to head the Jmrt program, which at that time was its infancy. Now that would have been very exciting. But just as Jmrt was in infancy, I was in my infancy too. And therefore, I thought that I should spend a few more years doing research. But sometimes I wish I had gone there. But sometimes I feel it was all right I didn't go. Because I didn't go to Bangalore, I landed in Pune. So Bangalore and Pune are in some respects twin cities. And I'm quite familiar with the local language in both cities, so I would have been equally happy in both places. But my trajectory would have been quite different if I had gone there at that time. But then I had a lot of contact with Swarup when he used to come to Bombay. And then when I stopped being a student and a postdoc and I was started working in TIFR, that was the time, let's say in the early 80s, when Swarup had started thinking about a new telescope. Now, at that time, he had many different ideas, including something called GERT, which is a giant equatorial radio telescope, which I believe he wanted to place in Nigeria. And then he used to sound out people about these things, even including people like me, who are far from being expert on the subject. And I remember a particular occasion when I had taken my young son, young meaning he must have been about 2 years old at the time, for a walk in the TIFR in the housing colony. And then Swarup came along and started talking to me. And then he kept talking for an hour or two. My son was quite patient. So he just sort of stood there through it. But I think that a couple of years after that, he told me that he's not going to do astronomy. So I wonder whether it was Govind's long astronomical discussion at that time, because Govind has inspired many people. And this one would be a first case of negative inspiration. I don't think that was the case because my son and I now are co-authors on papers. So then it continued like that for some time and we used to keep talking. And I remember a particular occasion when in the theoretical physics seminar room, there was a meeting again to discuss a new radio telescope, by which point I believe Swarup already had his ideas pretty well fixed. So, and then he also was thinking about teaching and was thinking about the joint program of teaching in between TIFR and Pune University. So there were quite a few people there from Pune University. And there was one person sitting next to me whom I'd never met before. And he seemed to be very enthusiastic and friendly. And he was broadly smiling at everybody. And then that was Professor Arun Nigwekar. And then he later became the Vice Chancellor of Pune University and Chairman of the University Grants Commission. And the thing which Justin mentioned about taking literature in all fields and all journals to the universities, that was a program which he set up and I executed with many colleagues. So then it was decided that Jmrt would be built, but the question was where would it be built, and whether in Indore or in Pune. I remember that Govind by then had already zeroed in on these two sites. And I suppose the main requirements were that there should be a sufficiently large plain surface available on which the antennae spread over 30 kilometers could be placed. And also there's the question of having good radio silence. Those were the days when cell phones were not known and not present. But one talked of other kinds of radio disturbances. And one reason for Govind choosing the low frequency band was there are two reasons. One is that it was relatively easier to build a great radio telescope to make low frequency observations than to build one for high frequency observations. And secondly, the skies were quieter, radio quieter in India than elsewhere. Now, these are the two things which motivated Govind Swarup to actually uh, build a low frequency radio telescope, and then he finally decided to come to Pune. So at that time, Professor Yeshpal and Professor Nalika were thinking of setting up a new institute for astronomy, and which would be mainly catering to the university sector, though it would be a research sector in its own right. And Nalika, I'm sure, could have gone to many places, but he was interested in coming to Pune. But the final decision was taken on the basis that the Jmrt center was to be located in Pune. So we came here, and Jayant and I, one day on the 1st of June 1989, we sat in Deccan Queen, left Bombay and came to Pune. And Professor Naresh Dadish was here at that time in the Department of Mathematics, and then we started building up IUCAA. So there are two institutes being built. I think that NCRA building was getting quite ready at that time. It was not known as NCRA at that time, it was just the Jmrt Center. But both of us, both the institutes were located in a building, with a very interesting building. There's the Lalit Kala Kendra of the Pune University, and it is a very beautiful building. I hope they declare it as a heritage structure so it doesn't get knocked down. And then the Jmrt Center had one room in that building, and IUCAA had another room in that building. And the rest of the rooms were devoted to Lalit Kala. And therefore, we could hear melodious music all the time, and the jhankar of payal with people dancing and so on. So it was, I didn't realize at that time what a divine thing that was. We were all very hectic up with setting up our own places. We didn't have enough chairs to sit on. And when the N+1 person came in, then one person had to get up to let that person sit down and so forth. Then the Jmrt Center moved to the new building. We followed them. We built a shed called Aditi, and we had IUCAA in it, but we also had 5 rooms in the Jmrt Center. We shared the library, but then the collaboration went much further than that, because we set up a joint program of lectures for graduate students, so the TIFR NCRA school, which continues to this day. And until recently, we used to also select students together, but that arrangement no longer holds. So it was Professor Nalika's idea, and which Professor Govind Swarup, of course, greatly supported, was to plug the university sector into the Jmrt project. That has happened to some extent. Hopefully, it will happen to even greater extent in the future, and the universities also get plugged into a SKA project. So I don't remember actually seeing Govind too often in those days, because he used to be moving around very fast everywhere, and he used to be at the Jmrt site and in Bombay and in Bangalore, and he used to be traveling very much. One incident I remember is that when Professor Lyndon Bell, who was a great astrophysicist, theoretical astrophysicist, one of the leading astrophysicists of our time, so he was visiting Pune IUCAA, and he said that when the famous Anglo-Australian telescope, which is an 4-meter optical telescope with which very great work has been done, and he said that when he went to the AAT site in Australia, in a very remote part of Australia, called Coonabarabran, he said that he had seen just a pit in the ground, which was where the foundation for the telescope was to be laid. And he said that he would like to see a Jmrt pit like that. And so Naresh and I took Lyndon Bell over to the site, and then he stood in a pit for one of the antennae, and we had taken this photograph. I don't know where that photograph is now. Try to locate it. So anyhow, I continued meeting Govind and discussing matters with him. That was a complicated affair. I mean, talking to him, because either he came and started talking to you and went on doing that, or you went to him because you wanted to say something and ask him some questions, get an approval or something like that. He listened to you for about half a minute, And after that, he started saying what he wanted. So typically what you had in mind hardly ever got said. But on the other hand, whatever he said was also very precious. You learned quite a lot from him. And his dedication to work, his enormous enthusiasm, his ability to take everyone with him. It is not very easy to get such a large project done. There are all kinds of problems, there are all kinds of ups and downs. But, uh, but the ability to carry people with you and then to deliver. Okay, so the proof of the delivery is not the inauguration of the telescope. I mean, that happens many times. Okay, but then there are problems which really don't allow the telescope to function to its limit. Now, that is hardly the case with the GMRT. Now, when many people, including several of the speakers of this session here, have worked very, very hard to get the GMRT going. And the world standard is that when that happens, you reserve a certain amount of time on the telescope for people who belong to the sector, who look after the telescope, who help build it. But that is not the case with the GMRT. The GMRT, all the time on the GMRT, is given out through proposals. You have to compete, you have to submit your proposals, which are vetted by an international committee, and then time is given. And every person in the world has equal rights on the time of the GMRT. Right? So therefore, but it is found that about 50% of the time he goes to Indian astronomers and 50% of the time goes to international astronomers, which shows two things. One is that Indian radio astronomers can compete at the world level, and that is number one. And number two is that people from all over the world have sustained interest in using the GMRT. The GMRT, of course, continues to go from strength to strength. We now already have the upgraded GMRT, and then the people in the GMRT center are making very critical, very critical contributions to building up of a square kilometer array, which is the radio telescope for the next generation. So there's an interesting thing which one can say here is that if you take an auto rickshaw to the Pune University campus and get off at a particular point there towards the back gate, which is about 3 kilometers from the front gate. So to the left of the road, we have got Ayuka. To the right of the road, we have NCRA. Okay, which so now in Ayuka, the software controls for the 30-meter telescope are being developed. That's to the left of the road, and to the right of the road, the software control system for the SK is being developed. Right, so this is, I believe, the only point on the earth at the present time where within 200 meters, these two enormous projects are taking shape. Right, so that shows the vision of Talikar and the vision of Govind Swarup, where we all came together and made all this possible. So they inspired us, they helped us, uh, they scolded us, they forced us to work very hard, and finally all this got done. Right, so therefore, Govind Swarup's legacy will continue to endure for decades. And Professor Dalikar still remains active, still remains inspiring. And he felt very, very sad when Govind left us because there was an enormous bond at the personal level here between Dalikar and Govind on the one hand, and then also people like us who were significantly younger than Govind, but who at least on occasion consider him as a friend, in addition to being in addition to being a mentor, a guide, and a philosopher. So that is all I would like to say. Thank you very much for providing me with this opportunity.
Thank you, Ajit. Thank you so much. We now move to the next speaker, Professor Yeshwanth Gupta. Professor Yeshwanth Gupta is the director of National Center for Radio Astrophysics in Pune. He did his PhD at TIFR, and he continued as a faculty member there. He has been the observatory director for the GMRT for almost 2 decades now, and has played a very key role in the upgrades that have taken place in this time, which keep the observatory competitive. Yeshwanth will talk about pulsars and the GMRT, and also how these were one of the key goals for the GMRT and what has been done with the instrument. Yeshwanth, over to you.
Thank you. And can you hear me?
Yes, we can hear you.
Okay. So let me say at the outset that it's a privilege to be invited here to talk about what I would say is one of my role models, Govind Swarup, and also to talk about an area of science with the Jmrt, which was both his dream and my passion. And so I'll share my screen. Okay, I hope you can see the screen.
Yes, yes, we can.
Okay, and so when the GMRT was conceived by Govind Swarup and team, and this is from the original paper, Current Science 1991, there were two key objectives that were outlined, and you can read them here. To detect highly redshifted 21 centimeter line of neutral hydrogen, and to be able to study a large number of millisecond pulsars in an attempt to detect primordial background gravitational radiation. And coincidentally, or probably not so coincidentally, these are the two topics that we'll be covering in this session. So I'm going to talk about the pulsar work with the GMRT and what we have achieved. And Jairam, after me, will tell you about what's been happening on the 21 centimeter studies. So one of the questions that is interesting is that an interferometric array like the GMRT, which has been talked about, is not ideally suited for pulsar studies, at least historically. And that's not what they were originally designed for. They're designed to give you high angular resolution by spreading out the antennas over large distances. And so, for example, the VLA, which was the archetypal interferometric array for many decades, never had the ability to observe pulsars. So this is where the foresight of Govind and others comes in. When the GMRT was designed, there was special care taken to build in the processing capability so that you could actually study pulsars with the GMRT. And that is what is called the phased array modes. And I'll talk very briefly about that. But not only that, we actually were able to turn this to an advantage for some aspects of pulsar studies, which would not be possible with large single dishes, which is what has traditionally been used for pulsar studies. And as a consequence, today, all interferometers in the world, all the modern telescopes have the ability to study pulsars. And I just illustrate this. I put this slide in just a few minutes ago after listening to Rajaram talking about the work that was done. But it also brings out what happens. And I won't go into the details of this, except to say that the processing of the signals from the antennas is done differently for interferometry to make the images and for studying pulsars with a special provision for just adding the signals from all the antennas to make it look like one big large bucket. And there are two different ways in which you can do it. I won't go into the details of that, but they allow different kinds of science to be done in coherent and phased array. And this is the part that was for the legacy GMRT system was done in collaboration with the colleagues from Raman Research Institute, as Rajaram was mentioning. So this was an important contribution from the RRI to the early days of the GMRT. And so when you do actually look at it and ask that what are the unique things about an array telescope, which you can actually use to advantage for studying pulsars. And one is, of course, that you can get a reasonably high sensitivity because you're just adding all the antennas like a large bucket, and then you can use that sensitivity for interesting studies like searching for new pulsars or studying pulsar emission in great detail. And then, as I said, you can add the signals from antennas in different manners, and that allows you extra capability of doing interesting follow-up of studies of pulsars. And I'll briefly touch upon that as we go along. And finally, if you do this properly, which is the way it was done with GMRT, you can do both the interferometric observations and the beamforming observations simultaneously. And there we'll see that how that brings some advantages for studying pulsars. And the other thing, of course, is that being multiple antennas, you can actually operate different antennas at different frequency bands of the observatory, and thereby allowing you to carry out simultaneous broadband multi-frequency observations, which is again quite important for trying to understand certain aspects of pulsars. And then again, I'll touch upon that also. And all this, as I said, was part of the original legacy Jmrt, but the upgrade that we recently finished has made many of these science goals even more powerful, and thereby giving the Jmrt a fairly unique position. So I'll just give just simple examples of what's been possible. So the sensitivity of the upgraded Jmrt now allows for all kinds of searches for pulsars to be done, and lots more pulsars are being found. With the legacy system, there were probably about less than 10 pulsars that were discovered, but today already the count is more like 40 pulsars that have been discovered with the Gmrt. And this is an example of one of the recent discoveries of the first new millisecond pulsar discovered with the upgraded Gmrt. In addition to pulsars, there is the not so distant cousins of pulsars called rapidly rotating transients, which are again signals that go on and off, but much more irregularly than the regular pulses from a pulsar. And again, these have become amenable for discovery with the upgraded Jmrt, and there are new results coming out in this also. This is one example of what you can do with the high sensitivity. And so pulsar emission has lots of structure in it. When you look at a single pulse, it has structure all the way, although the pulsar period may be of the order of a second and the pulse itself may be of the order of 100 milliseconds wide, it has actually structure all the way down to microseconds and perhaps even finer than that. And studying that in some detail can be very interesting to understand some aspects of the pulsar emission physics. And this is an example of doing that for the first time for millisecond pulsars, which are generally much weaker than a normal pulsars. And also you need much higher time resolution to go down and resolve the signal. But this was done, and one of the interesting results that this showed, so this is the Jmrt result compared to what is known in literature before, and you can see that one is able to extend the relationship down to much shorter rotation periods, which has interesting implications for trying to understand what are these entities in the pulsar magnetosphere that emit these very narrow micropulses. Moving from there to just talk a little bit about what's been done with the power of the different modes of beamforming. I'll take this as an example. So this is historically slightly out of context, but this is the first pulsar that was discovered with the Jmrt. And it was a thrilling experience. I was part of this team. And it turned out not only to be the first pulsar, but it turned out to be a very exotic pulsar, a binary pulsar in a very highly eccentric orbit with an eccentricity of almost 0.9, which was amazing. And it took a lot of effort and data analysis to actually infer that we were seeing this kind of a pulsar. But what was more interesting is that in order to follow up and get this result, you have to time the pulsar. And part of the timing is aided by being able to know where the pulsar is located accurately in the sky. And that is where this mode of being able to image simultaneously while taking pulsar data was utilized to great effect way back then in the early days. And so this is an optical image of the globular cluster in which we found this pulsar. And this is the radio image made with the Jmrt data from the interferometer taken simultaneously during the time when we were taking the beamformer data from which the pulsar was found. And you can see a single radio point source, which actually turned out to be the pulsar. And then you could get an accurate position of the pulsar from that, and that helps with the timing. And just to complete that story, with the upgraded Jmrt, which offers a much higher accuracy in timing, which I'll talk about in a minute, we were actually able to follow up this pulsar after a gap of 10 years. And with more accurate timing, we actually be able to work out what are the masses of the neutron star and the companion. And this may turn out to be the lightest millisecond pulsar with the precisely measured mass, and a tantalizing prospect that the companion may be another neutron star. So moving from there to just show how the interferometer and the combination of the beamformer can be used. In that case that I showed, you could see the point source for the pulsar very clearly, but in other cases, you see multiple point sources in the sky. And then you don't know which one of these is the target pulsar that you've just found. And then there are clever techniques that you can do where you can follow up each of these point sources and analyze the data separately, taken parallelly in a different mode, and then be able to quickly localize the pulsar location. The place where this has been pushed to the limit with the interferometric and beamforming capability of the Jmrt is to be able to actually make the map of the sky during the time when the pulsar is on and during the time when the pulsar is off. And that is really a somewhat intricate exercise, because you have to then collect the interferometric data separately. But if you can do that and you can subtract the two images, then you will see the image of the pulsar, because that is the time when it's on, and the image, and so the rest of the sky is empty, and you immediately able to localize where the pulsar is in the sky. So this is the kind of thing that really has been pioneered with the Jmrt. And there was an interesting offshoot of this, that there is often been this question that when you say pulsar is off, is there really no emission coming from the neutron star? And so this same technique of making the image when the pulsar is on and making the image when the pulsar is off can be used to see if there is any faint emission at the time when the pulsar is off. And then there are at least a few pulsars where this actually was found, that the pulsar is actually having a faint emission at the level of few percent of its on-source emission. So this again was enabled by this unique capability. Moving from there, I'll just talk a little bit about what's been done using the simultaneous multi-frequency capability. So what this means is that you can observe the same pulsar over a much wider range of frequencies. And one of the most interesting use of that, there are many other interesting uses about understanding the emission, but one of the most interesting use of this is to be able to measure what is called the dispersion measure, which is a property of the interstellar medium, which causes the pulsar signal to smear out. And to be able to correct for it with an accuracy of 1 part in 10 to the 5. And you may ask why such an accurate correction is required. And that is required for the use of these highly accurate millisecond pulsars in what is called a pulsar timing array in order to detect gravitational radiation. And I'll come to that as the last part of what has been going on. And this capability was significantly enhanced with the upgraded Jmrt, where we can actually observe over 200 megahertz of bandwidth compared to 32 megahertz with the old legacy system, simultaneously at different bands of the Jmrt. So here's an example for observation at 1260 to 1460, along with 300 to 500 megahertz data taken simultaneously. And you can then do this kind of measurement with much higher accuracy. And this has led to the group from India to start working towards joining what is called the International Pulsar Timing Array, whose major goal is to detect the gravitational background radiation by an accurate timing of a grid of such millisecond pulsars over many, many years. And the unique capability of the Jmrt will be to provide this correction term where the arrival time of the pulsar would be delayed because of the travel through the interstellar medium. And so these are some of the first results where we are able to get very good quality residuals and again get very accurate estimates of the dispersion measure, and are able to now begin to contribute to the international effort. And that is really that was the science goal that was mentioned in 1991 in the Jmrt paper. So with that, I'd like to end by saying that we do believe that the Jmrt is been living up to its promise of delivering quality pulsar science. And once again, the credit of foreseeing these capabilities goes to Govind Swarup and his leadership. Thank you.
Thank you. Thank you, Yeshwanth. Thank you so much. Our next speaker is Professor Rajaram Chengalur. He is also at the National Center for Radio Astrophysics.
hang on, I just need to stop sharing.
Yeah.
Yeah, done.
Yeah. Thank you. So Jairam has been working primarily on studying galaxies and also using mainly the hyperfine transition, the 21 centimeter line, which Rajaram mentioned, for studying galaxies, either in emission or in absorption, apart from doing a number of other studies at the Jmrt. He has also been involved in the last 10 years or so in a major upgrade of the Uti radio telescope, along with Professor C.R. Subramania, Somnath Bharadwaj, and others. In the interest of time, I request him to start his bit here.
Thank you, Jasjit. I hope you can.
Yes, we can see your screen.
You can see my screen, and I hope you can hear me too.
Yes.
All right. Yeah, I just wanted to start on a very slightly personal note that I would not be doing radio astronomy if I had not happened to meet Govind as an undergraduate. And so I'm grateful, for this opportunity to speak in his memory. So I'd been asked to speak about H1 studies with the Jmrt, past and present. And I'm actually going to spend a lot more time talking a little bit about the past, and in particular about the ideas that were there for this telescope, what kind of science it could do with the 21 centimeter line at the time that the telescope itself was proposed. So, but let me just step back and start with talking about what is this emission that we are interested in. Rajaram did mention a little bit about it, that basically atomic hydrogen emits a radio line, that is emission at a very specific frequency. And that is at a frequency of 1420 megahertz or a wavelength of about 21 centimeters. So if you have a gas cloud which is near to the Earth, it would be emitting radio waves at a wavelength of about 21 centimeters. But however, if this cloud is far away from us because the universe is expanding, that wavelength gets shifted to longer wavelengths, or it's called redshifted, basically, to lower frequencies. And because hydrogen gas is so abundant, the 21 centimeter line is relatively bright, and observations of this radio line allow you to study the evolution of atomic hydrogen across the universe. And for these reasons, it's formed a major part of the science goal of almost all radio telescopes which work at centimeter or longer wavelengths. And this has been the case for quite some time. So what I'm showing you over here is some very early pioneering observations by V. Radhakrishnan, who Rajaram also mentioned. He did this in Australia with an interferometer, which he had, I think, equipped with for this particular purpose himself. And it was to look at both the emission and the absorption of this 21 centimeter line in gas in our own galaxy. And I won't go into the details of this observation. I just put it up to show that the gas can be detected both in emission. Yes.
I think your slides are not moving. If you're going on to specific slides, you probably need to share the other window which has the presentation that you're cycling through.
Okay.
So it's stuck on the it's there now. Yeah.
So somehow in the full screen mode, it's not working. Yeah. Thank you, Yeshwanth, for that. Okay. Yeah. So I'll just continue in this mode where I don't go into the full screen mode. So yeah, so I think, most of what is in the slide I have already said, but you would not have seen this figure, which is basically the upper panel of the line in emission and the lower panel in absorption. And I put it up, mainly to show that the line can be detected in both emission and absorption, not just in our galaxy, but across the universe. And this particular observation actually was among those which were used by Radhakrishnan to show that the gas actually exists in multiple phases in our own galaxy. And then it turns out that this is the case typically of gas, hydrogen gas in galaxies across the universe. But now let me move on to the GMRT science case. That is, when the GMRT was being built, Yeshwanth showed that the current science paper, which highlighted two major science goals for the GMRT, one of which was pulsars and the other of which was to detect H1 from this atomic hydrogen or H1 emission from protoclusters in the early universe. And this science case was, along with all other science cases for the GMRT, were actually developed in quite a significant manner in the proposal for the GMRT, the official proposal for the GMRT, which is part of the NCRA archives, and it really makes for fascinating reading. So, but anyway, to get back to what our main theme over here, the protocluster search. At the time when the GMRT was proposed, there were two models for the formation of galaxies. One of them was called the top-down model, which was that large objects collapse first and then fragment to form galaxies. And the other was the bottom-up model, which is that very small objects collapsed first and then these then merged to form the galaxies. And these had, which of these two models would actually obtain depended on the nature of the dark matter. If the dark matter was what one would call hot, then you would have the top-down model, that is big structures collapsed first and then fragmented to form smaller things like galaxies. So you have protoclusters which form and then break up to form clusters of galaxies. In the bottom-up model, you have things which form, which are very small, and many thousands of them would then merge together to form the galaxies that you see around them today. At the time when the GMRT itself was proposed, the top-down model was the favored one, and in addition, it was there was a reasonable amount of theoretical understanding of the way in which this collapse would proceed. And it was understood that the collapsed objects would actually not be spherical, but they would be very flat. This was a calculation done by the great Russian astrophysicist Zeldovich. And so these objects were often referred to as Zeldovich pancakes. And so one of the main science goals for the GMRT was to detect these pancakes. And that was in part, of course, because this was one of the outstanding problems in astronomy at that time. And because of that, Govind had been interested in it for a very long time. So even prior to the GMRT, he had been interested in trying to detect atomic hydrogen from protoclusters. And he had Ravi Subramaniam, who also Rajaram referred to, who for his PhD thesis with Govind, worked on trying to detect protoclusters using the UTI radio telescope. Right, so given all this history, it isn't surprising that the search for H1 emission from protoclusters was an important part of the GMRT science case. And so I put up over here a sort of schematic showing you the distribution of antennas of the GMRT. There are 30 antennas altogether. And they're distributed in the following way, that you have about 18 antennas which are distributed in these Y-shaped arms over here. And the remainder are in a very compact core right at the center, which is about 1 kilometer by kilometer across. And that core was useful for a number of reasons. That core of antennas actually helped both in in the kind of beamforming pulsar observations that Yeshwanth was describing a short time ago. And also its size was well matched to the expected angular size of protoclusters. So if you wanted to detect the H1 emission from protoclusters, it would be the antennas in the core which would actually provide you the signal, which would be the most sensitive to this H1 emission. And if you look at the proposal, which was submitted for the GMRT, it actually had a strawman design for carrying out this search for protoclusters, where they spoke about, surveying about 50 square degrees of the sky in order to see whether one could detect protoclusters and then basically confirm whether the hot dark matter model or the top-down model was correct or not. But, and this is often the way things proceed in science, paradigms shift. By the time the GMRT was actually constructed, the top-down model was no longer favored. And this proposed survey for protoclusters was actually never carried out by the GMRT. But, and in this context, I think it's, something interesting that around the same time that the GMRT was getting built, there was in fact a claim for a detection of neutral hydrogen from a Zeldovich pancake. But by this time it was also, the top-down model was getting disfavored. And so it's, Govind and Kandaswamy Subramaniam from Ayuka actually had written a paper, looking at this claim detection to explain how in the bottom-up model, you might actually still see the kind of signal which was detected at this other telescope where it was understood to, where it was interpreted as being a signal from a protocluster, a Zelda-Rich pancake. Eventually, however, the detection itself was not confirmed, and it is now believed to be spurious. A major part of the science goal of the JMRT turned out to be, not very relevant by the time the JMRT was built, but this actually is not unusual for instruments. It's not unusual for instruments to be, the science case for an instrument to be partly superseded by the time the instrument is built. However, if you build that instrument carefully enough, you've designed it carefully enough, and it's sufficiently capable and flexible, it'll still deliver excellent science. And this is, of course, the case with the JMRT also. So, the first observations of neutral hydrogen done with the JMRT were actually not of, searching for protoclusters, but looking for the gas and absorption in the interstellar medium of distant galaxies. It led to the first paper, as well as the first thesis by Nissim Kanikar, which used JMRT observations. If you looked at the JMRT science case, although it highlighted this, search for protoclusters, it actually included many other, areas in which observations of the H1 21 centimeter lines could contribute, which was studies of nearby galaxies, to study the dynamics, to look at the dark matter in these galaxies, and so on. And the JMRT has indeed done a very significant amount of work in this area, both, used by national and international astronomers. The other interesting thing is that the JMRT science case actually also included a discussion of observations to check the bottom-up model, because as I said, at that time, there were two models. And although the top-down model was favored, the bottom-up model was there, and it did have clear predictions as to what, one might see. So in the bottom-up model, the collapsed objects were too small to detect individually. But interestingly, the collective fluctuations that they produce is in principle detectable. You couldn't detect any one object, but you could statistically detect, the emission from a collection of these objects. And I find it, very interesting that there was an observing plan in that very early science case, which spoke about using, again, a very interesting instrumental mode to try and make a statistical detection of these protogalactic clumps in the very early universe. And, statistical detection of H1 at high redshift, it turns out, has played, a major role at the JMRT. There are a number of groups which have been doing this. And in fact, statistical measurements of H1 at high redshifts, so-called what people call detecting the power spectrum of H1 fluctuations at high redshifts, is now an important science driver at many telescopes. At the JMRT itself, there have been groups led by Somnath Bharadwaj, as well as by Waley Penn and his collaborators, which have worked on this problem. The JMRT has also played a very leading role in a slightly different kind of stacking experiment, which is again statistically detecting the H1 emission and the H1 content of distant star-forming galaxies, even in a scenario where none of them can be individually detected, but still, you could detect on the average what their emission is, and that allows you to understand the properties of that population as a whole. And this is a program which has been ongoing for the last decade or so, and the upgrade to the JMRT has given a very major boost to this program. And so I'm showing you here now recent results from that. This is a paper published last year by Apurva Bera and collaborators, which include Jasjeet, and Nissim Kanikar, which has detected H1 at a redshift of 0.34 from galaxies, and that is, the first statistically significant detection of gas in emission, and therefore the gas content, the atomic gas content of star-forming galaxies at these redshifts. And since then, things have moved very rapidly. The Jmrt has now provided the first statistically significant measurement of the H1 content of star-forming galaxies at a redshift of 1. And that is, truly spectacular, because that is an epoch at which we know star formation is evolving very rapidly, and it's very interesting to know what is happening to the gas at these redshifts. So this was work which was sort of reaching its final stages of getting, accepted for publication just a couple of months ago. And Govind was, very, very interested in this. And every few weeks, until very recently, he would keep pinging to understand, where has this reached? Has it got through to publication yet, etc., and so on. And so, it is a little poignant that we are speaking now, in his memory. But anyway, I guess the main point I wanted to make was that something that Govind had actually envisaged 30 years ago about statistical detection of H1 at high redshift is sort of, still continuing to be a very major program at the Jmrt. There are proposals now to push to still higher redshifts. And I think all of this is basically a testament to the vision, not just, and over here particularly, I'm talking about the scientific vision. We've heard a lot about Govind's vision about building teams, building programs, building institutions, and so on and so forth. I did want to highlight also that his vision for science itself was also, off a tone with everything else. It was a very high quality, and it was clearly something which sort of, could last for decades. So that's where I'd like to end. Thank you.
Thank you, Jairam. Now we move to
just 1 minute.
Mr. Divya Oberoi, also from National Center for Radio Astrophysics, TIFR. So Divya is a solar astronomer. He studies the sun and its and the interplanetary medium, which is affected very strongly by solar flares and solar winds. He has been at the NCRA for almost a decade now. Prior to that, he was at MIT Haystack, where he was involved in building the first tile of the MWA radio telescope, which is now up and operational in Australia. He had done his PhD at NCRA. He was a part of the joint astronomy program that we heard about. And before that, he had done his bachelor's and master's at Delhi University. So, Divya, over to you.
Thank you so much, Jasjeet. So I must start by saying that I've been a very direct beneficiary of Govind's work. The JAP program, the Joint Astronomy Program, which you heard of earlier, was a program which I joined to do my PhD. I cut my teeth on radio astronomy at the Jmrt. I used the UT radio telescope to do my thesis work. I'm back for many, many years now at the NCRA, an institution which he established to pursue my dream of a career in astronomy. So it's really with a lot of sort of gratefulness and respect and regard that I share this presentation with you. And I would also like to thank the organizers for giving me this opportunity. So I'm trying to share my screen. I hope you can see it. Right. So I am now going to take you back. Right. We've last couple of talks, we have heard about what has come out of GMRT and where are we headed with that. I am now going to take you back to the start of Govind's own research career. That's when he was working on the sun. And to do that, it is useful to sort of set the stage by saying what was known about the radio sun back then, which as it turns out was not a whole lot. The fact that the sun emits in some other part of the electromagnetic band apart from the optical, which we have been aware of forever, it was discovered only in 1942. And that became the first band beyond optical in which people began to study the sun. And soon after its discovery, people were already aware of the fact that the radiation which was coming from the sun must correspond to, at least at the frequencies where it was discovered, must correspond to a medium of at about a temperature of 1,000,000 Kelvin. And this was a radiation which was very variable. So it was sort of described as disturbed, undisturbed, and an intermediate stage which was slowly varying. This emission had already been associated with the corona, and there was some understanding that this corona, what you see depends on the frequency at which you're observing, because this begins to turn opaque at meter wavelengths and shorter wavelengths. Paul Wild, who was also, I think, mentioned a bit earlier by KP, he had started routine observations of the sun by 1946. The very first interferometric observations of the sun were held by Martin Ryle in Cambridge and Paul Wild in Australia, which allowed you to figure out where is this emission coming from on the sun. And thus you were able to associate this sort of disturbed or storm emission coming from the vicinity of the so-called active regions or sunspots on the Earth. Next year, 1947, Ruby Payne Scott had discovered the fact that these bursty emissions or disturbed emissions, at least some of them, they drift from higher to lower frequencies. And by 1950, or actually the first time in 1950, the use of a spectrum analyzer, which could actually observe at a large range of frequencies at a given time, was introduced in solar astronomy. And soon after that, came the classification of these disturbed parts of the solar emission as types 1, 2, and 3. Okay, so this is where things stood, and Govind arrived in Australia in the March of 1953 after something like a 6-week voyage by sea. Okay, so here was one particular conundrum which was there, which became the first problem with which Govind worked on. So on the left, you see a theoretical prediction, which is based on the fact that the sun is surrounded by this hot gas. It's a gas which has a very strong gradient of density as you move further and further away from the sun. And because of this very strong density gradient, its refractive index is also changing. And if you were to trace a path through this solar corona, it would not be a straight line, but it would actually deviate. Based on detailed calculations of a medium like that, Smerd had come up with a prediction that you should see something like a limb brightening. Limb is nothing but the edge of the sun. Edge of the visible disk of the sun is what is referred to as the limb. So I'm just highlighting in my poor drawing the sort of limb brightening you would expect at something like 400 megahertz. The x-axis is distance from the center of the galaxy. Okay, and there are other frequencies which are shown there. So 400 megahertz, 1200 megahertz is here, 600 megahertz is somewhat intermediate. But the same year, there was an observation by Stanier from the Cambridge group, which actually found no trace of these of such a limb brightening at a frequency of 500 megahertz, which should be somewhere between 400 and 600 megahertz. Both of them show significant limb brightening. Okay. Now, like I said, Govind had arrived in Australia in the March of 1953. It had so happened that just the previous year, Christiansen and Warburton had completed the Potts Hill reservoir interferometer, which KP had mentioned earlier. And that was designed to work at a frequency of 1420 megahertz, at which, according to Smerd's prediction, you should see a very prominent limb brightening. And so I'm not sure if Govind was involved in taking these data or not. There is no clear mention of that, but data had been taken from about September of 53 to April of 54 from this interferometer. If you remember from KP's picture, it had a sort of east-west element and a north-south element, and the two of them were operating independently, and each of them is taking sort of one strip scan of the sun. So one is sort of integrating along east-west and looking at structures which might be present along the north-south direction, and the other is doing the reverse. And Christiansen assigned the job of combining these data to make a two-dimensional map of the sun to Govind. And the idea was to check if we can see this limb brightening and all. I won't go into the details, but this was, so the data was not digital. You had paper charts of from the Potts Hill Reservoir interferometer, and you had to digitize it manually, and you had to take Fourier transform twice after you had aligned these data taken together. It was a very painstaking job, and the result from that is what is seen on the image on the right. And all Govind got for all of that hard work was an acknowledgement in the paper, not even the authorship. Okay? But that was his sort of cutting teeth on interferometry for the first time here. Okay, the same pot cell grating array was then modified by Govind and Parthasarathy to work at 500 megahertz. The idea was that, okay, let's go to exactly the frequency at which the Cambridge group has not found the limb brightening and see what can we do there. And this is the result from their work, where they actually show the solid line is from the work of Govind and Parthasarathy, and the dashed line is what was published earlier by Steiner. So they basically, so he started by working on the frontier of the subject, something which was published in Nature. And here is a couple of people who don't even have their PhDs, who are sort of at that forefront and are contesting what has been presented by a well-established group. Okay, so I think from the very beginning, Govind was working at the frontier of whatever is it that he got involved with. So it was no surprise later that the problems he chose for the ORT and for the GMRT were all at the cutting edge of whatever was known in the world of astronomy at that time. Again, this is a picture which you saw in KP's presentation earlier. This is the discovery of the so-called U bursts, right? So what you see in this picture is time on the x-axis, and on the y-axis is frequency, where frequency is increasing from top to the bottom. Okay, and what it is showing you is that there is some emission which is taking place from the sun, which is starting at higher frequencies and drifting to lower frequencies, but then going back again to higher frequencies. Now we understand this as electrons, beams of electrons, which are traveling along coronal loops like this. We know that in the solar corona, the further away you go from the sun, the density is decreasing, and this emission happens to come out at a frequency which is proportional to the square root of the density, right? So we know that these electron beams are going to get accelerated somewhere here. I hope you can see my cursor, and then are going to travel along these loops. So while they are rising, you would see the frequency drift from a higher frequency to a lower frequency. But then when they start traversing the loop, if they happen to be traveling along a closed loop, which is going to bring them back to the sun, as they begin to come down, the frequency is going to shift from a lower frequency to a higher frequency. So this was the first observations of these rather rare sorts of bursts. Which made it to Nature. And so images like this were, of course, not available at that time. In fact, like I said, in the K coronagraph images, which are sort of ground-based coronagraph images, these things had not yet been detected. These sort of large loop structures of the sun had not yet been detected. Okay. Another very important contribution which came from Govind was the association of what is regarded as a typical measure of solar activity, which was the area of the sunspots, which happen to be there on the disk of the sun, with the flux, the radio flux, the energy being radiated by the sun in the radio waves. And he showed, these were again data from the pot-cell grating array, that as the area of the sunspots increased, which is plotted on the x-axis, the flux density being emanated by the sun in radio also tends to increase. And it's not a very clean correlation, but there is no doubt about the fact that as you proceed along the x-axis, you tend to rise higher on the y-axis as well. Now, this was a theme which he actually pursued in great detail in a lot of his work. So you can see from here that the difference in the flux density actually easily exceeds an order of magnitude from this plot. So the fact that there is a lot of variation in this had also been the reason why, for example, the earlier work from Steiner, he was not able to detect the limb brightening, was partly because his observations were contaminated by the active emissions from the sun, which completely drowned out the quiet sun emission which might have been there. And his was also a very painstaking work, where he had just one baseline where one of the antennas would be moved every day to take a measurement at a different baseline length. So Govind put in a lot of energy into trying to figure out how is the emission of these active regions, how does it change as a function of time. They would track the sun day after day, and they would see this pattern move across the sun, and they would be able to associate it with an active region. They worked a lot on figuring out what is the spectral structure of the emission which comes out from these regions. Though in view of time, I don't want to get into much detail about that. But the last thing I wanted to talk about here is some work which they did with the Kalyan Solar Radio Telescope, which was really the first uh, big interferometer, or maybe big is not the right word, but the first significant radio instrumentation to be set up in India. So on the left, you see sort of 16 16 consecutive days of observations. And each of those traces is actually a track of the sun. Okay, and the fact that the optical disk of the sun is smaller than the radio disk is sort of shown here, where the thick black line marks the visible disk of the sun. And if you look closely here, you would find that there are some peaks which sort of seem to shift their location day after day. And these are the ones which are coming from active regions, actually. So this work, these were again the pot-still dishes which KP had mentioned. By then they had arrived and had been put together. This was the facility which was set up by Swarup, working with Kapahi and Islur and Sinha. And these first results from Kalyan actually made it to Nature. They provided more evidence in favor of the limb brightening, once again at 50 centimeters or close to 50 centimeters. And they contributed to the studies of these active regions, determining their sizes and figuring out that the size of these active regions is actually significantly larger than the resolution of the instrument. So that was a very interesting contribution which came from here. There were other significant things which I'm just listing here without getting into any detail of them. So there was at Harvard, because they had an instrument which went in spectral coverage from about 100 megahertz to about 580 megahertz. They could cover a large part of the spectrum at any given time, but it was not an imaging instrument, it was a spectrometer. But using that, they observed a large number of different radio flares and tried to associate them with the presence or absence of sunspots on the sun. And that led to, it was a very detailed piece of work which led to some very interesting conclusions. Like I had said earlier, he'd been working on this slowly varying component of emission, which they associated clearly with the presence of sunspots. And there was a series of papers on that subject. And I think he also got Vijay Kapahi involved in some of that work. And another sort of different aspect which they considered, which Govind considered in his work, was about trying to come up with a theoretical model for what is giving rise to the emission from this slowly varying component of emission, which is always seemed to be associated with active regions. And there they used the idea that this is most likely gyroresonance emission, which is coming from here. Okay. Yeah, and with that, I'll stop. Thank you.
Thank you, Divya.
So,
yeah. So now it is my turn to speak a little bit. I am going to essentially summarize what we have heard from all the different talks, trying to put together a thread. If we look at Govind's research career, Govind's career in India, if we focus on that one, then what we see is that he clearly wanted to work on problems which were cutting edge, and he was not averse to taking help from people. He persuaded the Australian group to donate radio dishes, the entire setup, which we just saw pictures of in Kalyan, which was used for observations of the sun. And then he proceeded to build a large-scale facility like Ooty to do cutting-edge work in a very, very different area, using occultations by the moon to uncover and understand structure of radio sources. This is I don't know how many of you have seen pictures, not just the pictures which we saw today, which essentially show a small segment of the Ooty radio telescope. The Ooty radio telescope is 500 meters long and 30 meters wide. It takes up better part of a hill. And if you go look at Google Maps, you will find Ooty radio telescope clearly visible
in satellite pictures of that region. You delve a little deeper and you realize that it is not that just he built such a large thing in one go. There were many experiments which were done. There were 2 trial cylinders which were built in the region, which still exist, which one can go and see. And all the technologies, all the things which they wanted to do were tested on the smaller cylinders before they built the large scale facility. In the process of building this, he clearly realized, building and using the facility, he clearly realized that we need a different kind of training for astronomers than is available in typical graduate schools in places like the Tata Institute of Fundamental Research. And he proceeded to set up the Joint Astronomy Program. He realized that a facility like UTI, the UTI radio telescope, requires a number of people working on it. And he roped in the Raman Research Institute group, who contributed significantly to developments in UTI, as well as overall developments in radio astronomy in India. And as he realized limitations of the UTI kind of radio telescope, he was quick to make proposals for initially for international collaborations, where they will build a large array, which essentially that dream has matured and has now become the square kilometer array. But Govind realized that time was perhaps not ripe for a large international collaboration of this kind at that stage. And he pitched for the GMRT and built that facility in Pune. One has to keep in mind that the economy, when UTI radio telescope was built or when GMRT was built, was not so good, or the foreign exchange reserves were not so good that one could import things, one could import technology. So pretty much everything was designed, tested, and built in India. And it's a facility which both the facilities were world class. GMRT, when it was finally completed, it became an open facility where astronomers from anywhere in the world can make a proposal, ask for telescope time, and there is an independent time allocation committee which is set up by the National Center for Radio Astrophysics, which does this job of time allocation. And it is this kind of an open competition which has led to brilliant science coming out of GMRT. Kudos also to Govind's successors, who have made sure that the telescope remains competitive. They have all contributed in diverse ways to make sure that we can extract more and more out of the same instrument. Of course, all of this makes use of developments in computing as well as in electronics, which were not available when GMRT was first conceived and designed. But it is nice to see that that thread of making use of the latest technology to extract the best science out of the instrument and involve people all over continues. Govind, just like with Joint Astronomy Program, at some stage in 1990s realized that there is a need for people not with science or engineering, but both. And of institutes like ICERS, in his own conception, institutes where students will study basic sciences and then in later years have full freedom to jump between engineering and basic sciences and do a lot of research along the way in order to mature as scientists. He started working on this proposal in mid-1990s. It took a long time to get before it got traction. And finally, the proposal was heard at the highest levels in early part of 2000s. In 2003, the proposals were being considered as, so the proposal of what we call today as ICERS was being thought of as National Institute of Science. And there was a proposal to have 4 such institutes, one of them in Allahabad. I happened to be in the Harishchandra Research Institute at Allahabad at that time. And when this discussion was going on, Govind got hold of me and said that, look, if this comes up, you have to contribute. Okay, whether HRI contributes or not, you have to contribute and you have to be available. And of course, I have always had interest in teaching, and that is why I shifted to ICER when it finally came into being. Unfortunately, the plan for National Institutes of Science could not be implemented, and it had to wait another couple of years before it took shape as Indian Institutes of Science Education and Research. And Govind continued in pushing for engagement with engineering and interaction between science and engineering through and through. Although in the later part, that the engineering component was dropped at some stage. In the last 12 years or so, I mean, I have been at ISA Mohali for 10 years. And in these 10 years, certainly, whenever we met, he would ask about how ISAs were progressing and talk about what kind of courses we are offering, what kind of research opportunities we are offering to students. And his engagement with ISAs remained as active as his engagement with GMRT, as his engagement with radio astronomy in general, and so on. So I would like to stop on that note and request Dharamveer ji to give his vote of thanks.
It is pleasure to propose a vote of.
Yes, we can hear you.
Okay. Thank you very much for giving us an opportunity to associate with such a distinguished gathering, as well as paying tribute to Professor Govind Swarup. He can aptly, as some of you described, father of radio astronomy in India.
Dharamveer, can I just intervene? I just received a message that a meeting parallel to ours is on at Pune in honor of Govind Swarup. So what a coincidence. 2 meetings running parallel in honor of Govind Swarup. One from north of India, other from Pune.
From the west of India.
West of India.
Okay, that shows the monumental work that he did.
The meeting at Pune is at Vigyan Bharati, and it is being attended by Dr. Kakotkar, Dr. Mashalkar, Vijay Bhatkar, Yeshwanth Gupta was present there as well, and also the IOCA director Shamak Rai Chaudhary, and it was anchored by Air Marshal Bhushan Gokhale. So it's parallel in all respects. You know, we have a similar set of people, and you are now going to conclude on our behalf.
Well, it has been a pleasure associating with this meeting. I learned a lot about the contribution of Professor Govind Swarup. I just mentioned give a personal note before I say something else. It was in 1971 when I did MSc from IIT Kanpur. I went to Tata Institute to do PhD in solid state physics. And then they interviewed me and they said that the vacancy is already full. So they offered me to work at Ooty for radio astronomy. That was in 1971. Perhaps Tata Institute or Government of India were planning to set up whatever is there right now, Ooty. So I declined. So now I feel it was a golden opportunity that I missed. And I realized more when I went to Green Bank astronomy, radio astronomy observatory. My son was working somewhere near to that place, so he took me to that observatory. So I felt that we had started working well in time, quite ahead of several other countries. And more so when India was planning to launch several initiatives on space missions. And I'm sure Professor Swarup's work would have been quite useful to our space programs. I would also like to say 2 things, especially to the distinguished scientists and scientific administrators. It is high time that we start spreading information about the monumental work done by our people within our own country. There is hardly any subject or any paper or any kind of a small module in schools or colleges or universities where we give overview of the contribution of Indian scientists and engineers. except remembering some of the contribution like Bhagla Dam or a few others, Visheshwarya, etc. But I think it is high time that we take a policy decision to highlight the work of our own people and remember them. So finally, I would say that thanks to Professor Grover, Professor Bhagla for giving us this opportunity.
So Dhanavir, may I request you to invite Vinod Sani if he wants to add anything? He has been...
Oh, sure, Professor. Okay, I'm sorry. Professor Sani, I would request you to add wherever I have left or whatever you wish to.
No, thank you, Dhanavir. First of all, I must compliment you for arranging this event. I have known Professor Govind Swarup because I was in the training school when he just started this program on radio astronomy. And Dr. Raman had, in fact, just as you missed an opportunity of working in radio astronomy, Dr. Raman, in our final placement interview, had told me, why don't you look at radio astronomy? I said, I know nothing about it. I can't. And Velusamy finally joined from our batch, that illustrious gathering of people, including people like Kapahi, who built that Uti telescope and later on were associated with Jmrt. Now, I had, as director at Indore, in our Center for Advanced Technology, I knew who are the people who are opinion makers in the country. And at every opportunity, I would call one or the other of them. I mean, I definitely called Professor Menon, Professor Yashpal, I called Kasturi Rangan and so on, S.K. Joshi. So on one occasion for the National Laser Symposium, I requested Professor Govind Swarup whether he would be available for the inaugural session. Govind put a precondition. He said, provided you do something for the students. So I think it was so close to his heart, and that resonated with me today. When I watched a lot of people mentioning a variety of things, I think he was a passionate Indian, a passionate educationist. And I can also share with you one thing. See, as somebody who belonged to TIFR in those days in which Govind Swarup was working, there was a very intense collaboration between BARC and TIFR. And in fact, one name which comes to my mind is S.N. Sheshadri, who had been encouraged by Vikram Sarabhai to build actually the satellite tracking station at RV. And he built the control system for it. And I think Govind Swarup tapped into that capability, which Sheshadri had. And there was a fairly intense collaboration between people in TIFR and people in BARC. On a larger note, exactly the sentiments which you expressed, Dharamveer, I think we need to advertise our illustrious past and somehow ask what is it which we need to do to actually brighten our future. Because when you talk to young people today, they don't seem to be as enthused. But whatever I have heard today, of course, a lot of it was difficult for me to completely absorb, tells me that we have a lot to boast about our achievements. And I think if the younger people know a little more about it, presumably we'll attract many more. So I want to compliment both Arun, you and Kea for arranging this event. And of course, pay my homage to Professor Govind Swarup, for whom I have a very high place in my heart. Thank you.
Yeah, if you don't mind, Grover Saab, I'll just take half a minute or 1 minute. That is, you see, we can, if Grover is able to take it through, we like to organize a series of lectures of the contribution of Indian scientists who have, like Professor Swarup, Dr. Bhabha, and many others. Their contribution need to be highlighted. I can tell you very frankly, even after doing MSc in physics, I did not know that there were people like Govind Swarup in our own country. So I think there is a need to highlight the achievement of our own people. I heard about this observatory in the USA, not within India. I mean, that is something which I felt honored in a way, because they said you're doing monumental work. And at Greenbank. In fact, I learned that there is some such observatory. So, and that was in 2010. So I went to UT 2014. I visited the observatory. I said, I must visit. Somebody had mentioned to me in Virginia. So all that I'm trying to emphasize upon all of you who have been involved and who are still involved, we should carry the success stories of our own people. We should take pride in the work that our people have done, not only in the science, technology, in many other disciplines. So I would be happy from the Society for Promotion of Science and Technology. If you wish to come out, we can find some resources to come out with a book. It is my offer. I will leave it to some of you who are willing to take this opportunity.
That's an excellent idea. The only thing is, I would say it should be in the form of some short films, which are easier to watch if you really want to entice people.
No, sure. I mean, whatever format, the issue is, how do we take it forward to the people, to the students, to the younger generation?
So allow me to share this thought. You go back in the old days, the films division used to, in fact, once in a while make clips about some of the scientific activities. Today, except for Doordarshan, which does a little bit of that once in a while, maybe Saturday, Sunday. Otherwise, the thing has been completely eclipsed. So maybe we have to prod a few more people, at least,
No, the entire media, entire younger generation is hooked on to the TV. That fellow who has got, who died, the entire Sushant. I mean, look at the priorities of Indian public. I mean, the entire media is buzzed with the Sushant.
No.
There have been murders and deaths all over the country. But was he a very distinguished person who made valuable contribution? I mean, even Mahatma Gandhi would not have got that much of mileage.
Coverage. Well, that's
on the TV. So it's a sad reflection of our society.
Yeah, but I think you have run a wonderful event. So let's end on an optimistic note.
And please take us for granted. If you wish to organize, just tell us. We'll be there with you.
Okay. Thank you. Thank you again.
And I'm grateful to all of you.
Thank you
for sparing your time.
Thanks, Vinod, for joining.
Thank you so much. No, my pleasure. I had to go out in between because.
नहीं आपके बिना ये चलना नहीं था प्रोग्राम आप लोगों
नहीं thank you for the opportunity to share my thoughts
and
also.
Thanks to Grover.
Thanks also to people who joined on YouTube. I can see quite a few of our earlier students, mentors of our summer schools from ICERS and from Pilani and from other places. So thank you everybody. There's somebody from Ahmedabad. There are quite a few distinguished scientists I can see. So thanks to all of them. Thanks to all of you.
And Bagla Saab ko dhanyawad.
Bagla Saab, of course.
Thanks to SPTI and Bagla ji.
Yeah, thanks to all the organizers. It was a wonderful opportunity. Thank you so much.
Thanks to all the speakers.
All right.
Okay.
All right.
Bye-bye.
Thank you.
Thank
Have
you.
a nice day.
Yeah, you too. Bye.
Thanks. Bye.